Welcome. You're about to listen to a presentation by Professor Dr. Ertugrul Taciroglu, Department Chair at the Civil and Environmental Engineering Department at UCLA. The presentation of Ertugrul Taciroglu was part of the program of the third panel organized by CHARE as part of the panel series Turkey and Syria after the earthquakes. Next to his function as Department Chair at the Civil and Environmental Engineering Department at UCLA, Ertugrul is the inaugural chief editor of the multidisciplinary Journal of Civil Engineering. He serves on editorial boards of several journals, including Earthquake Spectra, Soil Dynamics and Earthquake Engineering, and Structural Control and Health Monitoring. Dr. Taciroglu is also a fellow graduate of Istanbul Technical University, and he holds a master's and PhD degree from the University of Illinois. Dr. Taciroglu is also a fellow graduate of Istanbul Technical University, and he holds a master's and PhD degree from the University of Illinois at Urbana-Champaign. He completed postdoctoral research at the Center for Simulation of Advanced Rockets. Dr. Taciroglu's research interests span the disciplines of theoretical and applied mechanics and structural and geotechnical earthquake engineering. He is currently conducting projects on regional performance-based risk assessment of civil infrastructure under natural hazards and structural health and performance monitoring. Dr. Taciroglu is the recipient of a National Science Foundation Career Award and the Walter Huber Prize of the American Society of Civil Engineers, where he is a member of the Engineering Mechanics Institute Board and Governors.
Thank you very much. So let me just confirm that you hear my voice well and you're able to see my screen.
Yep, you're good.
All right. I think I heard like three different pronunciations of the effort here. So I heard care, kare, and chare. I vote for the last one. I think it's a great effort, and thank you for inviting me to speak in this very interesting panel. As Professor Çelik, my background is in structural earthquake engineering, as you've heard. So some of the elements of my presentations will bear similarities to his presentation, but I hope there's additional takeaways. So when engineers think about hazard resilience, they think about it in the terms of this kind of diagram where the horizontal axis is time and the vertical axis is the functionality of a civil infrastructure element that you're thinking about. If the stakeholders improving the performance of this element, its functionality will increase over time naturally. But of course, typically what happens is that it ages and its functionality naturally declines. But assuming that you have some baseline functionality, an event like an earthquake happens and it reduces the functionality of this infrastructure component, maybe it's a water conveyance system or communication system, etc. And the danger is that if the resilience of the system is not high, its robustness is not high enough, it can hit rock bottom and it will collapse. And it will provide, no recovery options for you. Hopefully, it has some capacity at the end of the event and it will kind of recover. And the idea of this panel is obviously to explore ways in which this recovery can be expedited and also perhaps use this as an opportunity to build the system back better with higher performance and put it on a nice positive trajectory. Of course, civil engineers will not just work on these diagrams. We typically put numbers on these things and actually do compute some scalar value of functionality and resilience. But this is an extremely challenging task. And I will argue here that even the current best research institutes don't have the ability to actually compute the resilience in a meaningful way. The challenge is not, when you're looking at a single infrastructure system, but rather when you realize that you have to look at many infrastructure systems that are all coupled with each other. And this is even not counting the social, economic, and other aspects of resilience. So it's a very, very challenging task. And it borders on the state of the art in research and capabilities. And it is part of the reason why we are, as a society in general, not just in Turkey or the US, but around the world, not able to achieve resilience in a meaningful way yet. So what is the problem at hand? If you look at the exposure to earthquakes in for example, the state of California, which is where I'm right now, we have these best available estimates of what may happen in the future. So on the left-hand side, you're looking at the tectonic faults in California, and the color indicates their probabilities of producing a certain magnitude of earthquake, which are summarized in the tables on the right-hand side. So if you look at these tables and ask yourself, well, what is the likelihood of experiencing a very large magnitude earthquake in California that will create some devastation? You'll see that it's almost guaranteed, 100% within a 30-year period. What that means is that if you're thinking about your infrastructure system as a stakeholder, you understand that during the service life of that infrastructure element, it is almost guaranteed to have a large earthquake. So you have to be ready for it. The problem is there are other decision makers that will help you achieve this resilience, say the governor of California. And a typical governor of California will serve like 5 years, 6 years, maybe 2 terms. And that is much less than the kind of the return period of these major earthquakes in a given region. And that's why there's always a tendency to kind of kick the can down the road. And it is one of the parts and of the puzzle of resilience. Like, how do we get ourselves ready for an event that is very rare, because kicking the can down the road is so super easy. So my perception on how to achieve seismic resilience, which will draw many parallels to what Professor Çelik mentioned and also other speakers have mentioned. So again, you'll see some repetition there, but I hope there's some additional elements. First of all, I'm going to be kind of talking about obviously seismic resilience, but you can unplug the seismic hazard and you can plug in other hazards like floods, wildfires, which is something we're being exposed to more and more in, for example, the state of California, hurricanes, et cetera. So I think if you have developed capabilities to achieve resilience in one area, it can translate to other hazards as well. So the number one thing that you have to do is to understand the hazard itself. You need to be able to go to a specific location in your country, in your region, and be able to understand the probabilities of experiencing different magnitudes of earthquakes. And in the US, it is, I think, currently a well-done effort. Southern California Earthquake Center, Pacific Earthquake Engineering Research Institute, USGS, United States Geological Survey, have been collecting data for many, many years. And we're able to come up with those maps that I've shown you, with which you can compute this sort of probabilistic seismic hazard analysis. Because if you don't know your exposure, like, the hazard that you're going to be exposed to, you're going to be either overspending or going to be unsafe with the structures that you're building. To be able to achieve this level of prediction, you have to have an extensive network of ground stations that collect data from ongoing earthquakes so that you can create a database and data-driven models. In the US, you can see on the map of California, the density of the ground stations that measure earthquakes, and they've been collecting data for the last 60, 80 years. That's quite a long period of time, and that allowed us to develop some probabilistic models. Japan has a much higher density, of course, has a much higher population density as well. This is not possible for most countries in the world. And then, you have another way to solve the problem. Turkey has a relatively good extensive network, although it has to be really increased by a lot because it's a large country supporting a large population. But it doesn't have enough seismic data from the past. And this kind of data gap can be filled with computer simulations. We have physics-based simulations of wave propagation on Earth. And access to supercomputers is far easier these days. So you can do really high-end simulations to fill in the data gaps, especially for large earthquakes that have not been observed very frequently. So the next element of seismic resilience is to develop effective and enforceable seismic design guidelines. By effective, I mean they should work. When they are enacted, they will do the job. And enforceable means that it cannot be just overly optimistic or too hard to satisfy, because then people will start finding ways around it. And of course, if it's not enforceable, it will be useless. So for that, I think you have to come up with seismic design guidelines that are tiered. At the top tier, you have to have high performance criteria for your critical infrastructure. By that, I mean lifeline systems. major viaducts, bridges, hospitals, emergency response centers, dams, any kind of system like that. And for them, you have to do your best so that they will survive the worst earthquake with almost no damage and become operational or continue their operations. For that, you can utilize high-end technologies. They're not necessarily cheap, but over the life of an infrastructure element, they amortize themselves quite easily. So use seismic isolation bearings, use high-performance ductile concrete, so you can survive these earthquakes without any scratch. And that is a goal that can be achieved. For everything else, I will just kind of summarize the idea that everything else should just not collapse at all. And this is especially true for buildings. So you have to have some non-collapse criteria, and that can be enforced and effectively done. So as you can see, there are two examples of this. One is the set of buildings that collapsed. And then another one that kind of suffered really kind of damage, not just because of the earthquake only, but I think the other building kind of knocked on it as well. And it survived the earthquake. And this is the kind of design we have to have. It has to, okay, bear some damage, but just save the lives of the inhabitants from these major rare earthquakes. And at the very bottom, you have the rural construction, which is almost unguided and unregulated. Even for that, there are best practices. And then there are some organizations that kind of try to educate populations around the world, from Nepal to Africa and other places, that can be used. And parallel examples can be developed in Turkey to improve very rural construction, so that even that can also kind of save lives. In a nutshell and in summary, a tiered seismic design guideline would look like this, where your most important structures are slated to be operational for the rarest earthquakes even, and your the least important structures, say warehouses or plastic toys from China, okay, they can collapse. I mean, they can suffer really heavy damage, and you can spend less money on them. And this kind of tiering will allow you to kind of achieve resilience. I think it's one of the must-haves. And I will say that the Turkish design guidelines are more or less like this. Okay, the current state of the Turkish design guidelines are about the same idea, have the same idea. The next element of resilience is to embrace new technologies and investing in research. There are new materials, new construction techniques that I think would be satisfying both sustainability as well as seismic resilience. And these technologies are new, and the basic assumption of it's new, it must be more expensive. But in reality, over the lifetime of a structure, it is really much cheaper, especially when you consider that it may save lives. I would like to highlight among these things two things. One is the timber structures. Of course, it is a new sort of sustainable type of design, and it is taking off in the US. People are striving to come up with tall buildings that are made with timber, and they're going to, withstand the lateral forces of an earthquake. So, we have to embrace these kinds of technologies. The other one that I'd like to highlight is masonry structures. Typically, when a civil structural engineer goes to school and wants to specialize, and they want to have a safe and comfortable job working for a big company, they'll focus on either steel or concrete. Masonry doesn't really bring a lot of funds. But let's remember that a lot of the historical structures we have are masonry structures. So we really need to find ways to incentivize education and research advances in that area, so we can protect our cultural heritage in addition to some of the rural structures we have. But embrace new technologies. You have to do that to achieve seismic resilience. The other puzzle in the seismic resilience question is kind of looking backward, which is, in fact, most of our exposure. I'm not really worried about the new construction that is being built in Turkey as much as, of course, worried about what exists already. So we really need to understand and communicate the risks to the occupants, to the government agencies, et cetera, about the exposure we have. For that, we have to kind of develop model inventories and show them realistic results. How do you build model inventories to do assessment? It is a difficult job because it involves millions of buildings, hundreds of thousands of bridges, et cetera. And it is a monumental job. But using modern technologies, machine learning, computer vision techniques, and all the extensive data that companies like Google, Amazon, Yandex have been collecting with their cars, driving around, taking those pictures. You can actually automate this process and be able to come up with approximate building inventories for any region you look at. Here you see some examples of us extracting metadata from images to build models of bridges in California and buildings in California to do seismic resilience assessments. In fact, we have recently applied this technology to buildings in Istanbul in the Zeytinburnu districts, and we kind of modeled 16,000 buildings from street view images and satellite imagery, created approximate models. On a one-to-one basis, they're not going to be super accurate, but on a regional basis, they can be quite accurate. The reason we picked Zeytinburnu district was that because we already had metadata about this region from a government study, a municipality study in the past, so that we can compare the accuracy of our results. I'm not going to get into the details of any of these things, but I just wanted to say that these kinds of regional studies are possible. And then the other thing is addressing the vulnerabilities that you discover or uncover through these assessment studies. And of course, you have to do retrofits and replacements. The retrofit is obvious, but it's not always cost effective. Here you see examples of retrofitting soft story buildings in Los Angeles. There are thousands of buildings like this identified, and they're on a time clock to retrofit or demolish. So you have to put programs in place like this to put people, the owners, on notice to either satisfy, either retrofit their systems or replace them. And of course, we're familiar with the government subsidized housing projects in Turkey. So that is a point of discussion I think this panel would serve well to do, because like if the government is doing, are they just looking at only seismic resilience? Because building better means that you need to be resilient to other hazards as well and satisfy other criteria, use this as an opportunity. I think government could use some direction there. I think it is clear how we can build seismically safe buildings. There's not a lot of huge amount of research needed there, but when you want to build them both seismically resilient and sustainable and satisfy other criteria that I'm not an expert of, okay, then now you have to kind of start brainstorming. So again, as the first speaker mentioned, and Professor Çelik also touched upon, you need to be able to do assessment at a regional scale because, and I'll show you some shortcomings here today. Building back better means not just building back the building inventory better, but also maybe our human resources better prepared, building them also as better engineers. When we go to engineers and take classes at Istanbul Technical University, they'll teach you excellent classes in steel design, concrete design, etc. And then you can go ahead and build your buildings to become seismically efficient and all of that. But all these buildings are part of an ecosystem, right? They're in an urban environment, they're interconnected with their environment. And just looking at them from that perspective, sorry, my animations are being messed up a little bit. Let me just click through them. They're connected to an environment and the entire region gets affected. And you need to have the big picture to be able to achieve total resilience. And so that you can come up with reasonable actuarial plans. The insurance companies would need this information and, do better urban planning and also better emergency response planning. Sorry, let me just scroll through this. I think I have extensive animations there to go to the last point. Sorry, I was over enthusiastic about my animations, I suppose. But let me just kind of show you on this graph. So the built environment is highly interconnected and it contains all these elements that are connected with each other. And let me just give you this example. Let's say that you're a civil engineer and you designed a hospital. And this hospital is perfectly designed with base isolation and it will just survive the worst earthquake without even getting windows cracked, which may be fine. But if you remember that this hospital is connected to the region, and if the bridges that connected to the surrounding region are collapsed and the power goes down, the patients cannot go there, then the functionality of the hospital, is nil. So you cannot think of the resilience from an individual element by element basis. You have to really look at the big picture. And only then you can kind of really understand your exposure and quantify the things that you need to do. So going back to my presentation scheme, the other elements of seismic resilience is to develop rapid post-event damage assessment technologies. This is very important. And I think the basic thing that you need to do there is to do seismic instrumentation of your structures. With seismic instrumentation, you can quickly tell if a building suffered any kind of damage, it needs to be evacuated or can continue its functionality. And also it can help you direct the first responders to the right places. This technology has matured and it can be deployed. And I think Turkey would do well to kind of adopt these technologies. They're not as expensive anymore. Today, you're buying a car. Imagine you're buying a car that has no fuel gauge. You know, that would be just unthinkable, right? You're driving the car until you run out of fuel. And only then you realize, oh, I ran out of fuel. That's a car without a sensor. So you're not buying cars without sensors. Don't build new buildings, especially critical infrastructure like hospitals, bridges, without seismic instrumentation. And you know, it addresses this problem of post-event decision-making. Do we need to stop the operation of a network? When will it be safe to restart the operations? Where do we send the first responders? And can we quickly assess the structural damage, which has many sub-questions? One is, well, is there damage in the system? That's the detection question. Then what are the damage components? That's the localization question. And finally, the most important one, how much damage is there? You know, if you're looking at a collapsed building or, you know, that's not hard to classify, obviously. But what we're looking at is something more devious than that, which is, well, a building looks damaged, but is it safe to occupy or should we vacate it? That's the kind of question that can be answered with the help of sensors. Especially in urban regions, this is a monumental task that cannot be achieved without seismic instrumentation. Case in point, in a Tohoku earthquake in Japan, just the Shinkansen rail line, and you know that they have many companies, just them have had to inspect 750 locations to be able to start their operations. Seismic instrumentation can also eliminate objective human-based inspections and also allow you to opine on, you know, hidden damages and pile foundation systems, tunnel linings, et cetera, which is impossible to do with only visual inspections. The last element there in rapid post-event assessment is to develop technologies with which you can scan an entire area, be able to understand the extent of damage quickly. So in this recent earthquakes, we used the government labels, which were, I guess, generously shared with the public, so we could see which building was labeled as what damage level. And we went to the satellite location of that, and then we trained an artificial intelligence network. And we were able to obtain very high accuracy from satellite images on classifying the level of building damage. On the right-hand side at the bottom, you see this kind of probability distribution function of the damage levels. And you can see if it's like a total collapse, it's almost, you know, super 100% accurate. The satellite imagery can be quickly classified. And if it is a more sort of lesser damage, we can still do that with, of course, higher uncertainty. But if you have access to these kinds of technologies, you should deploy them and be ready to deploy them and be ready to share them with the rest of the world so that they can also do some rapid post-event assessment. This is totally automated. It can be done in minutes as long as you have access to satellite imagery. And of course, hazard resilience, the last element there is that it can only be achieved and accelerated through collaboration. It involves multiple disciplines, as we heard many times today. Civil infrastructure resilience, the built environment resilience is only one part of the puzzle. And of course, you know, we have our advances there and knowledge gaps, but resilience can only be assessed through its multiple dimensions. And if one part is really weak, it may mean the collapse of the entire system. So it can only be done in a collaborative environment. So not only we have to kind of think about this from building back better, but also from a human resources perspective, when we think about these kinds of hazards, we should educate our students, our future engineers and architects so that they understand the interfaces of these disciplines, so that when they sit around a table, they don't have to start from the scratch and start learning each other's terminologies. We have to really kind of build it into our education system. Whatever we learn from one hazard can, I think, translate quite well to other hazards, whether it's wildfires or floods that, you know, we are seeing more and more due to climate change. Of course, another element there is to engage multiple countries so that we can share data, knowledge, technologies, and resources, and even beyond seismic. Just 2 days ago, I was in Morocco. As you may know, they suffered an earthquake there. You know, maybe 5,000 lives were lost. And when you just kind of think about Morocco, they're interested in doing something about seismic resilience. But other African countries that were present there, they were not really so interested in it. But when you look at the big map of Africa, if you look at an individual country, the probability of them suffering an earthquake is low, but combined as a continent, it's very high. So this means that if they form a sort of a brotherhood, sisterhood of seismic resilience, including everyone else in the Mediterranean basin, we can develop technologies and solutions in a much more meaningful way, sustainable way.